In this section, you will learn how to do the differentiation of the inverse trig functions. First up, let's do a review of inverse trig functions. And to kick that off, let's start out with the reference angle chart for the special angles in quadrant 1, which are pi over 6, pi over 4, and pi over 3. Now, sine of theta is as easy as 1, 2, 3. And that's how we can fill in these values very quickly. Cosine theta then is just 3, 2, 1. And then you can visualize. You know that sine theta divided by cosine theta gives you tangent of theta. So just take 1/2, divide it by radical 3 over 2. You would get 1 over rad 3, which when you rationalize is rad 3 over 3. Or rad 2 over itself is 1. Rad 3 over 2 over 1/2 is rad 3. So very quickly, you can come up with the reference angle chart, and then you can use those reference angle trig function values to find the trig function values in other quadrants. Here we have a table of domains and ranges for all 6 inverse trig functions. You will see arcsine of x and sine inverse of x used interchangeably. So this notation is equivalent to this notation. Now all the ranges of the inverse trig functions you can see are some version of negative pi over 2 to pi over 2 or 0 to pi. Sometimes they exclude the endpoint values, as with arctangent and arccotangent. Sometimes they exclude the midpoint value, for example here, pi over 2, and here, for cosecant inverse of x, it's excluding the y value of 0. But essentially, you can summarize all of these ranges with this visually easy to understand chart. So cosine inverse, cotangent inverse, and secant inverse essentially live in quadrants 1 and 2 from 0 to pi. You can see cosine inverse lives 0 to pi for its output values. Cotangent inverse lives 0 to pi, just not including the endpoints, 0 or pi. And secant inverse lives from 0 to pi, skipping over pi over 2. Now in your trig class, you went into great detail for why this is true, and you can refer to my trigonometry videos on my YouTube channel for chapter 6 if you would like a more thorough review of the inverse trig functions. Here, in quadrants 1 and 4, will live sine inverse, tangent inverse, and cosecant inverse. And notice that all 3 of those live from negative pi over 2 to positive pi over 2. Here's sine inverse. It lives quadrants 4 and 1 from negative pi over 2 to pi over 2. Tangent inverse lives from negative pi over 2 to pi over 2, just not including those endpoints. And cosecant inverse lives from negative pi over 2 to pi over 2, excluding 0. Rather than memorizing all the little different intricacies of these ranges, you can visualize it on this coordinate plane here. Now, if you are taking the inverse trig function of any positive value, then you will give an answer in quadrant 1 that's between 0 and pi over 2. If you are taking the cosine inverse, cotangent inverse, or secant inverse of a negative value, then the answer that you give, in other words, the output, will be an angle between pi over 2 and pi. Whereas if you take the sine inverse of a negative, the tangent inverse of a negative value or the cosecant inverse of a negative value, then you will output an angle in quadrant 4 between negative pi over 2 and 0. So let's give this a try. In this example, we have to find each exact value. First up, we have the arcsine of radical 2 over 2. So when you're thinking about this, remember that the output of an inverse trig function is an angle. So if the arcsine of radical 2 over 2 is equal to theta, then picture taking the sine of both sides of this equation, the sine of the arcsine of radical 2 over 2 would just be radical 2 over 2. And of course, taking the sine of the right-hand side, we would have sine of theta. Now remember that when you're taking the arcsine of a positive value, then that means your answer, which is your angle, has to be in quadrant 1 between 0 and pi over 2. So your job is to think of what angle that if I took the sine of it, it would output a value of radical 2 over 2. And looking at the special angle chart, that angle is going to be pi over 4. Here, if we do the arcsine of negative half, we know this is going to output an angle, and now take the sine of both sides of this equation. Taking the sine of the arcsine of negative a half leaves us with negative a half, and we have that equals sine theta on the right-hand side. Because we are taking the arcsine of a negative value, we know that our angle has to be in quadrant 4 between negative pi over 2 and 0. So we have to give an answer that's in this range. We look at our reference angle chart and see that a reference angle of pi over 6 has a sine that would be a half. Putting it in quadrant 4 in our range, we would get negative pi over 6. It's time to check your understanding, so pause the video to try these other examples on your own, then restart the video when you are ready to check your answers. Here we have the arcsecant of 2. We know that's going to output an angle. If I take the secant of the left-hand side, it equals 2. If I take the secant of the right-hand side, I have secant theta. It might be easier for you to think in terms of cosine. So if I take the reciprocal of the right-hand side, I need to take the reciprocal of the left-hand side. For secant inverse of a positive, we know that our answer is going to have to be in quadrant 1. So the angle in quadrant 1, whose cosine would be a half, we look at the reference angle chart. That reference angle is pi over 3. In quadrant 1, that's just pi over 3. Here, for arc cosine of negative half, remember that it will output an angle. If I take the cosine of the left-hand side, I get negative 1/2. If I take the cosine of the right-hand side, I have cosine theta. We look at our reference angle chart, and if the cosine of the angle is a half, the reference angle is going to be pi over 3. When you're doing the cosine inverse of a negative value, you know that your angle will have to live in quadrant 2. The quadrant 2 angle, whose reference angle is pi over 3, is going to be 2 pi over 3. For arctangent of negative rad 3, remember it will output an angle. Take the tangent of the left-hand side. You are left with negative rad 3. Take the tangent of the right-hand side. You have tangent theta. Looking at our reference angle chart, if the tangent is radical 3, the reference angle is pi over 3. Because we are taking the arctangent of a negative, we know that our angle has to be in quadrant 4, in between negative pi over 2 and 0. Our reference angle is pi over 3, so that means our angle is negative pi over 3. Here, for arc cotangent of negative 1, it's going to output an angle. Take the cotangent of both sides, and we would have negative 1 is equal to cotangent of theta. If you prefer to think in terms of the tangent, that's okay too. Take the reciprocal of the right-hand side, we get tangent theta. Take the reciprocal of the left-hand side, it remains negative 1. Now the arc cotangent, or the inverse cotangent, of negative 1 means that that angle has to live in quadrant 2. Your answer is going to be between pi over 2 and pi. Using the special angle chart for reference angles, you see that the reference angle is pi over 4. So if you have a reference angle of pi over 4 in quadrant 2, you know that your angle is 3 pi over 4. In part 2, you will learn how to evaluate expressions and solve equations with inverse trig functions. In this example, we have to evaluate the tangent of the arcsine of 2/3. Remember that an inverse trig function outputs an angle, and if that angle is the arcsine of 2/3, then that means the sine of theta equals 2/3, because I took the sine of both sides. We can draw a picture of this angle. Here's theta. If the sine of theta is 2/3, that means the opposite side is 2, the hypotenuse is 3, and this leg over here is going to be the square root of the hypotenuse squared minus the other leg squared. So this is equal to radical 5. So what this problem is asking us to do is to find the tangent of this angle. And the tangent of theta we know is defined to be the opposite leg, which is 2, divided by the adjacent leg, which is radical 5. We can rationalize this very easily and see that the solution is 2 radical 5 over 5. In this example, we have to solve arctangent of the quantity 2x minus 3 is equal to pi over 4. To get at the variable of x, we need to undo the arctangent, and the way that would happen is to take the tangent of both sides. So we take the tangent of arctan of the quantity 2x minus 3 on the left-hand side, and then we have to take the tangent of pi over 4 on the right-hand side. Tangent and arctangent are inverse functions, so they undo each other. We have 2x minus 3 on the left-hand side. Tangent of pi over 4 is equal to 1. And now it's a simple algebra problem. Add 3 to both sides. We have 2x equals 4. Divide by 2. We get x is equal to 2. In this example, we have to write an algebraic expression for the tangent of arc cosecant of 3 over x. And remember that the arc cosecant of 3 over x is going to output an angle. And if we say that angle is equal to the arc cosecant of 3 over x, I can take the cosecant of both sides and have cosecant theta equals 3 over x. And if I'm more comfortable thinking in terms of sine, I can take the reciprocal of the left-hand side, turn it into sine theta, take the reciprocal of the right-hand side, and turn it into x over 3. Now we can draw a picture of theta. If the sine of theta is x over 3, that means the opposite leg is x, and the hypotenuse is 3, and the adjacent leg here then would be the square root of 9 minus x squared, because you take the hypotenuse squared minus that other leg squared. So then this problem is just asking us to find the tangent of that angle that we called theta. So that's going to be the opposite leg, which is x, over the adjacent leg, which is square root 9 minus x squared. And if we are asked to rationalize it, we multiply by 1 in the form of square root 9 minus x squared over itself. And this becomes x radical 9 minus x squared over 9 minus x squared. In this example, we have to solve the arcsine of x is equal to the arc cosine of x. Now the technique here is to get x isolated on one side. For example, we could choose to isolate it on the left side. So we take the sine of the left side, arcsine x, which means we then have to take the sine of the right-hand side, arc cosine x. Now what we will do here is the left-hand side simplifies to be x, and on the right-hand side we're going to do a substitution where we let theta equal the arc cosine of x which of course translates into, if I take the cosine of both sides, we get cosine theta equals x, and we can draw a picture. If this is theta, we know that the cosine is the adjacent leg over the hypotenuse, so that's going to be x over 1, which then means the opposite leg is going to be the square root of 1 minus x squared. If we do that substitution, then that means this right-hand side will simplify to be sine theta. Bring down the left-hand side, x equals. Now we use our diagram to find that sine of theta is the opposite leg, which is radical 1 minus x squared, over the hypotenuse, which is 1. And this is using the diagram. So now we have x is equal to the square root of 1 minus x squared. And to solve for x, we would want to square both sides. Now, one thing to remember from your trig class and your algebra class is that if you square both sides, you will need to check for extraneous solutions. So now the left-hand side becomes x squared equals the right-hand side, which is 1 minus x squared. Add x squared to both sides, so we now have 2x squared is equal to 1, which means x squared is equal to 1/2, which means x is equal to plus or minus the square root of 1/2, which if we rationalize is equal to plus or minus radical 2 over 2. Now remember that when you square both sides, you have to check for extraneous solutions. So let's try these two. If we let x equal radical 2 over 2, and then let's check it in the original equation, we would have arcsine of radical 2 over 2. Does that equal arc cosine of radical 2 over 2? And the arcsine of rad 2 over 2 is pi over 4. The arc cosine of rad 2 over 2 is also pi over 4. Those two are equal, so this one works. Let's check x equals negative rad 2 over 2. We would have to do arcsine of negative rad 2 over 2. Does that equal arc cosine of negative rad 2 over 2? The arcsine of negative rad 2 over 2 is negative pi over 4. The arc cosine of negative rad 2 over 2 is 3 pi over 4. Those two are not equal to each other, so we have to reject this solution. So the only solution here was that x is equal to radical 2 over 2. So now in part 3, we look at the derivatives of inverse trig functions. Consider the derivative with respect to x of the arcsine of u. And we're going to do that substitution we've been doing where we let theta equal arcsine u. So then that means what we are going to be finding here is the derivative with respect to x of theta. Now if theta is the arcsine of u, then that means that sine theta is equal to u, which is the same as u over 1. And now we can draw a picture. Here's theta. Get our right angle in there. If the sine of theta is u, that means the opposite leg is u, the hypotenuse is 1, and the adjacent leg would be 1 minus u squared. Now we're trying to find the derivative with respect to x of theta, or we could call this d theta dx. What we're going to do is start off with this equation where we have sine theta is equal to u. And then we are going to take the derivative with respect to x of both sides. So we have derivative with respect to x of sine theta is going to be the derivative with respect to x of u. Now the left-hand side, we know derivative of sine theta with respect to x would be cosine theta d theta dx. Remember implicit differentiation. When the variable doesn't match the variable in the denominator of your derivative, you have to tack on that chain rule part, d theta dx. Now on the right hand side, we just have du dx. Now let's solve for d theta dx. We would have d theta dx is equal to du dx, and of course we would have to divide by cosine, so I'll multiply by 1 over cosine theta, and now we have d theta dx is equal to 1 over cosine theta is the secant of theta, and then I'm going to put this du dx over here, calling it u prime. Now if we look at our diagram and get secant of theta from the diagram, we know secant theta is hypotenuse divided by the adjacent leg, so that's 1 over the square root of 1 minus u squared, and then we have times u prime. And remember who d theta dx was. D theta dx is just equal to the derivative with respect to x of arcsine of u. So we just learned that the derivative with respect to x of the arcsine of u is equal to, we could write it like this if we want, u prime over the square root of 1 minus u squared. We just proved that the derivative of arcsine of x is u prime over the square root of 1 minus u squared. And in similar fashion, the derivatives of the other 5 inverse trig functions can be derived. Our goal here now is to be able to use these formulas finding derivatives. And one good thing that you can notice is that they come in pairs. The derivative of cosine inverse is just the opposite of the derivative of sine inverse. And the derivative of cotangent inverse is just the opposite of the derivative of tangent inverse, etc. So really, you have 3 sets that you have to learn. So now, in this example, we have to find the derivative of f of x equals arc cosine of x squared. The rule that we will apply is negative u prime over the square root of 1 minus u squared. So then f prime of x is going to equal negative u prime, so that would be negative 2x over the square root of 1 minus u squared. And remember, u is x squared, so we have to take x squared and square it. So this is equal to negative 2x over the square root of 1 minus x to the 4th. In this example, g of x is equal to arctan of radical x, and we have to find g prime of x. The rule that we will apply is u prime over 1 plus u squared. So then g prime of x is going to equal, u prime here means we have to take the derivative of x to the 1/2, which would be 1/2 x to the negative 1/2 over 1 plus u squared in the denominator, so 1 plus radical x squared. And then this is going to equal, let's get our fraction bar in there. The only thing that's going to remain in the numerator is 1, because this 2 has to go to the denominator. This x to the negative half goes into the denominator as square root of x, and then that has to multiply 1 plus x. In this next example, h of x is equal to arcsecant 2x over x. The rule for finding the derivative of arcsecant is u prime over absolute value of u square root of u squared minus 1. So then h prime of x is going to equal, let's make a big fraction bar here. Now remember, we will also have to use the quotient rule in order to find u prime. So we'll have to do f prime g minus f g prime over g squared. So the derivative of the top is derivative of arcsecant of 2x. So we'll be using this rule here. So u prime is 2 over absolute value of u is absolute value of 2x, and then square root of u squared minus 1 will be square root of 2x squared minus 1. Then we have to take that times g, the denominator, which is x, minus f, which is arcsecant 2x, times the derivative of the denominator, which is 1, nice that it's a simple one, over the denominator squared, so over x squared. Let's pull this 1 over x squared out front. And see what we can do to simplify on the inside. Now we have a 2 in the numerator here, and we have an absolute value of 2 in the denominator. Well, absolute value of 2 is 2, so these 2's are going to cancel. We will have an x in the numerator. That absolute value of x stays in the denominator, times square root of 4x squared minus 1. And then we have to subtract arcsecant of 2x. And that's all we'll do to simplify this one. In this example, we have to find the derivative of g of x equals x times the square root of the quantity 16 minus x squared minus 16 arcsine of the quantity x over 4. Well, g prime of x is going to equal, looking at this first term here, we see that we will need the product rule. So the derivative of the first would be 1 times the second. I'm going to write that as 16 minus x squared to the half, plus the first, which is x, times the derivative of the second. So that's going to be 1/2 times 16 minus x squared to the negative half. Then the chain rule says we have to take that times the derivative of what's inside, which would be negative 2x. Then we have this subtraction and a constant of 16. And now we have to find the derivative of arcsine of x over 4. And the rule for that is going to be u prime over the square root of 1 minus u squared. So we will be multiplying by u prime, which would be 1/4, over the square root of 1 minus u squared would be x over 4 squared. So let's start to clean this up. We will get the quantity 16 minus x squared to the half. Now in this second term, we have a negative sign, so we will be subtracting. The 1/2 times 2 becomes 1. The x times x gives us x squared. And then we have the quantity 16 minus x squared to the negative half minus 16 times 1/4 is going to give us 4 over the square root of 1 minus x squared over 16. Now something we will want to do is simplify this complex fraction here. And we want to get rid of this denominator here of 16, but remember it's under a radical. So we can multiply by 1 in this form. Think of it as square root of 16 in the denominator, and think of it as 4 in the numerator, because 4 over the square root of 16, which is also 4, this whole thing is just 1. So all we are doing here is multiplying by 1. So now we have the quantity 16 minus x squared to the 1/2 minus x squared times 16 minus x squared to the negative 1/2. And now this will become minus, in the numerator we have 4 times 4, which is 16. In the denominator, underneath the radical, we have 16 times 1, which is 16, and then 16 times a negative x squared over 16 means we're subtracting x squared. Let's continue to simplify. We have 16 minus x squared, that quantity to the 1/2 minus x squared times the quantity 16 minus x squared to the negative 1/2 minus this coefficient here of 16. And then if we bring this radical to the numerator, it becomes the quantity 16 minus x squared to the negative 1/2. Now these two are like terms, and we can combine them. So we are going to get the quantity 16 minus x squared to the 1/2. Now we can factor out a negative, so let's put the minus sign there, and we can factor out a quantity 16 minus x squared to the negative 1/2. Then we would have left the x squared from here, from that first term. And then be careful with the signs here. Because we have a minus sign here and we need a minus sign here, we have to put a plus sign here. And we've already factored out this part of it, so we just have left that 16. Now we can factor out a quantity 16 minus x squared to the negative 1/2 from this first term. We will have a quantity 16 minus x squared to the 1, so we don't need to write that exponent. And double check it. The quantity to the negative 1/2 times the same quantity to the 1 would be that quantity to the positive 1/2. Now we have that minus sign. We have factored out this quantity 16 minus x squared to the negative 1/2, which means we just have left the quantity x squared plus 16. And this is going to equal, let's get a fraction bar going. This quantity 16 minus x squared to the negative 1/2 heads to the denominator as 16 minus x squared to the positive 1/2. In the numerator, we've got 16 minus x squared from that first term. Then we have to distribute this negative sign. So we get minus x squared and minus 16. And finally, in the numerator, this 16 will cancel with the minus 16, and we have a negative 2x squared left. And in the denominator, we can either leave it as a fractional exponent, or we could choose to write it as the square root of 16 minus x squared. Either one is fine.